So today we will do QR decomposition. QR decomposition is another way to solve overdetermined systems, and I shall illustrate that with some examples. And there are some other students joining. Anyway, so what we will do is full QR decomposition, reduced QR decomposition, and I'll show you why this new technique to solve overdetermined systems that I will introduce gives you the same solution as the least square solutions method. The pseudo-inverse method provides the two solutions are identical, and we will see why. And then I will introduce you to an algorithm called the Gram-Schmidt orthogonalization algorithm that does reduce QR decomposition. Okay, so now we have a matrix M by N. The number of rows is more than the number of columns. So this is a tall matrix. Okay, and then we will factorize A into this form. Q, and this R0 here, Q is a M by M unitary matrix. You know what's a unitary matrix? All its columns are mutually orthogonal, and the columns are also unit vectors, right? That's what makes Q a unitary matrix. And what's one of the important properties of a unitary matrix? Its transpose is equal to its inverse. And then here, A equals Q, R0. This R here is a M by N upper triangular matrix. Actually, this is N by N. This R here is a N by N matrix. This R0 here, if when you're doing full QR decomposition, normally this entire block vector is referred to as R, in which case that would be an M by N matrix. Otherwise, if you're looking at only this smaller square matrix, it's N by N, which is equal to number of columns of N. Okay, and this is upper triangular. So this is what it looks like. Let me express Q in terms of its columns. So Q1, Q2 until Qm. Remember, M is the larger one and N is the smaller one. So Q1 through Qm. And what's the size of this? Each of these vectors, column vectors, is also M, right? Each of these is also M dimensional. And then this is the upper triangular matrix block R, R11, R12 until R1n. Because it's upper triangular, the lower triangular elements are 0. So I have 0, R22 until R2n, and so on. In the last row of this R, the nth row, N as in Nebraska, 0, 0, all zeros except the last element, RNN, the diagonal element. And then we have all zeros here. Each row of this is 0. Okay, so this is the form of the full QR decomposition. And graphically, this is what it looks like. A equals Q, and this is R. And its upper part, a square matrix, is upper triangular. And then this lower part of this is all zeros. Okay, and now when we do the multiplication, Q1 is going to get multiplied by R11, R12 until R1n, right? To get the rows of, to get this, A. And then Q1, sorry, what is it? Q1 is going to get multiplied by R11. And Q2 is going to get multiplied by this, R22 until R2n. Now, look at the last one, Qm here. Since these are all zeros, so Qm here is going to get multiplied by all zeros, correct? In fact, the previous one is also going to get multiplied by all zeros. In fact, we're going to multiply whole bunch of these Qs, columns of this unitary matrix Q with zeros. So they are kind of redundant, right? Therefore, these are going to get multiplied with these. These are the columns of Q, which are all going to get multiplied with zeros when we do this matrix multiplication. Therefore, this is what I have. A equals Q1 until Qn. I'm taking the number of columns is n. So Q1 through Qn, and then Qn plus 1 through Qn. So Q1 through Qn are getting multiplied with this elements of this R. And all these columns, Qn plus 1 through Qm, are going to get multiplied with zeros. So they really have no meaning, except to make this matrix Q a unitary matrix, right? And so these columns of Q are kind of redundant. So we can simply drop them and write A equals, we're just taking the first N as in Nebraska elements of rows of Q. Q1 through Qn, and this is R. And now this Q is not the original unitary matrix, it's a M by N matrix now. This is the new Q, it's an M by N matrix. So it's a tall matrix, the same size as A, and this is R. I'm dropping all these zeros here. And I've dropped from the original Q, which was a unitary matrix, I dropped columns n plus 1 through m, as in misery. So I'm left with this. And this Q is not a square matrix. It's in fact a tall matrix, right? So it cannot be a unitary matrix. This is what it looks like. This is the reduced QR decomposition. A equals, this is my reduced QR decomposition Q, which is no longer a unitary matrix because it's not even a square matrix. And this is the upper triangular matrix R. Okay. Now Q has less columns now. So Q transpose Q is still equal to I because the columns of Q are still orthogonal, but Q transpose is no longer equal to I. This, in fact, Q is, what's the rank of Q? The rank of Q will be smaller of the two numbers, right? M and N, Missouri and Nebraska. So it will be Nebraska. N. Q transpose Q will give you I, but Q transpose will not be a full rank matrix. It will be a matrix of rank M. Although it's an M by N matrix, the rank of this matrix will be N, hence Q transpose is no longer equal to the identity matrix. Okay, any questions so far?
No.
This Q here, keep this in mind. In full QR decomposition, it will refer to a unitary square matrix, and in reduced QR decomposition, this will be a matrix, a tall matrix with some of the columns of the original unitary matrix dropped. Okay, now how do we solve overdetermined systems? Now, in the last lecture, we addressed the sum square error, and we chose X to minimize the sum square error. Are you guys able to hear me?
Yes.
Yes, we can hear you.
And are you able to see the screen?
Yeah, we can see.
Oh, because my screen somehow went blank.
No.
Uh, okay, we're back. So you're able to see the screen, right? Hello?
Yeah.
Yes.
Okay, good. So, let's see how we can solve overdetermined systems. And I'll just check if we are getting recorded. Yeah. So remember, we have in an overdetermined system, less number of variables and more number of equalities to satisfy, right? So A is a tall matrix and X is a n by 1 matrix, and we should try to match AX with B, but we cannot do that because we have less number of variables at our disposal. And so what we try to do, if you remember the last lecture, we took the error or the residue AX minus B, and we try to minimize the squared L2 norm of AX minus B, the difference, correct? And that was the sum squared error or minimization method, or the min norm method. So now let's see how we solve the same system of equations using QR decomposition. So we have AX is approximately equal to B. We want to satisfy these, but we won't be able to satisfy it completely because we have more expressions than variables. So what we do is we use the full QR decomposition. This is the full QR decomposition. So QR0x is equal to B is what we want to solve. 3 multiplying both sides with Q transpose. Now Q transpose is a full rank and it's a square matrix. So pre-multiplying both sides with Q transpose, what do we get? Q transpose Q R0x is equal to Q transpose B. I have this approximately equal to sign because we cannot solve this precisely. Okay. Since Q transpose Q is I, the identity matrix, we have R0 times X equals Q transpose B. Right? And remembering that Q is the big M by M matrix, so what is Q transpose B? It will be a M as in Missouri, a big long vector, right? Okay. So let us express Q transpose B in this form. Q transpose B is a block vector of size M as in Missouri times 1. And we will break it up into 2 parts. C1, which will contain the first M as in Nebraska elements of this Q transpose B, and the remaining M minus N elements will be C2. Okay? So if that's Q transpose B, then what we have is R0x is approximately equal to C1, C2. So reading off the first N, N as in Nebraska, N rows, Rx equals C1. And R is a upper triangular square matrix, right? And so it can be inverted right away. And I'll show you back substitution, how to solve expressions like this, where R is upper triangular or lower triangular. I'll show you how to do it. Okay, so X is R inverse C1. That's what we get. But somehow if we equate the bottom M minus N elements, if you look at these rows, the bottom rows, we have 0 on this side. We're multiplying 0 with X, and here we have C2, and 0 and C2 on this side. That's why we have this approximate. We cannot make 0 equal to C2. Okay, but anyway, this is the method. What we are doing is we're simply ignoring these elements C2, the second block of Q transpose B. And we are solving X equals R inverse C1 using back substitution. Okay, any questions so far?
No.
Now R is upper triangular. Okay. So this is the steps to solve an overdetermined system using QR decomposition, using full QR decomposition. So we factorize this A into Q and R0, and then this side B, we take the first N as in Nebraska elements, and then we solve Rx is equal to C1. Using back substitution, we get X equals R inverse C1. Okay. Now we can use reduced QR decomposition too. All we have to, it will automatically, when we do Q transpose, it will give you C1 because we have already dropped the rightmost columns of Q. Okay. So we can use reduced QR decomposition right away. So this is reduced QR decomposition. What we have is AX is approximately B, QRX is, this is reduced QR now. QRX is approximately equal to B, whence RX is approximately equal to Q transpose B. Q transpose Q is still the identity matrix, which Q transpose B will give you C1. This will be only C1. This is the full Q. This is the unitary matrix Q, and this is the long matrix Q. This is this Q, and this is this Q. Okay, so this is how you approach overdetermined systems using QR decomposition. Hence, X, it will give you the same answer. X is R inverse C1. Here's an example. And this example I will use later on to build up on why this QR decomposition method to solve overdetermined systems gives you the same solution X as the sum squared error solution or the min norm solution that we did in the previous lecture. How did we solve it in the previous lecture? We took the pseudo inverse of A, right? X is equal to pseudo inverse of A times B is what we did in the last lecture. Okay, so here is, I'll use this example. R0X is approximately equal to C. Let this be R. Instead of upper triangular, I've used lower triangular. Okay, it doesn't make much of a difference. It'll illustrate the same point. So I want to solve this equation. Okay, now I do the multiplication. Oh, actually, what I do is I take the difference between the left and right and the square norm of that. Okay, and then I do the multiplication and the simplification, it yields this. This is the square norm of squared L2 norm of this R0X minus C. Okay, now what's the solution? How do you minimize this with respect to X1 and X2? We let X1 equals half and X2 equals X1, right? Half is the optimal solution, correct? And this would be the min norm solution because we're trying to minimize the norm. Are you guys with me?
Yes.
Everybody?
Sorry, Dr. Rosa, I didn't catch that with the minimum of that.
Okay, so we want to solve this equation.
Yes.
Okay, so let's say this is my R, this 2 by 2 matrix here, 2, 0, negative 1, 1, and 0 is the 0, 0. And X1, X2 equals C is 1, 0, negative 3. Okay, I want to solve this, but this is an overdetermined system because we have 3 equations and only 2 variables. right?
Mm.
So the difference between the two is this. The squared L2 norm of the difference is what we want to minimize. That's
Yeah.
equal to R. Remember, R equals B minus AX originally. What we have is,
Yes. Yeah, I remember that.
hmm?
Yeah, I remember that part. Yeah.
Okay, so, okay.
But for minimize that
Oh, so this, let's do, we simplified this and we get this expression here. This is equal to the L2 norm. Okay, we do the matrix multiplication and then take the square of all the elements and add them up together. This is what we get.
yes.
Okay, in fact, you can see that twice x1 minus 1 squared plus negative x1 plus x2, that's x1 minus or x2 minus x1 minus 0, or same thing as x1 minus x2 squared, and then 0 x1 plus 0 x2 minus of minus 3, which is 3 squared. Okay, so that's the squared L2 norm of this vector on the of this vector, the difference between these two. How do I minimize this with respect to x1 and x2? I want to minimize this quadratic with respect to x1 and x2. I can make this equal to 0 and this equal to 0, correct? These two terms I can make equal to 0. These are squares, so they can, this, what's on the right hand side, can never be less than 3 squared, correct?
Yeah.
So
Yes.
if I solve this and this, I will get 3 squared. 9. This squared L2 norm can never be lower than 9. The minimum is 9, right? So how do we get 9? By letting x1 equals half and x2 equals x1, which is half. That way, both these terms become zeros. Okay.
Yeah, I understand, Dr. Thank you.
And now, what I told you is we'll just ignore the last few rows of this 0 times x equals C2, right? So let's just drop the last, in this case, this 0 is actually just a row vector, right? This one, 0, 0. So we just drop it and we only look at R, x1, x2, and we again ignore this negative 3 here. C2 is negative 3 here. C1 is 1, 0, 1, 0. Okay, if we just ignore the last rows, the redundant rows, then we get this, right? And if we solve this, we get, again, the same solution as this one. It will admit the same values of x1 and x2. They have the same minimum. Okay, so this is why I can effectively, if you go back here, this 0x and C2 here, these rows I just ignore and solve for Rx is approximately equal to C1 or Rx equal to C1 here. Okay, so all I have to do here is, instead of doing the whole thing, I can drop this last row here, 0, 0 from this side and negative 3 from this side. So I have a good neat square matrix here, which is also a triangular matrix. And then I can directly solve for it. It's a square matrix, and I can use my back substitution to solve for it. And I will get the same solution as the min norm solution, at least in this example. Am I clear? So this should give you some insights into the equivalence between the QR decomposition method to solve overdetermined systems and the min norm solution, or the sum square error solution, the minimum of the sum square error solution. Both are equivalent. Okay, now we'll go formally to the proof. So is the method that we get from QR decomposition is the solution, the same as the min-norm solution. So the min-norm solution would be this, right? We take B minus AX is the residue, and we take the norm of that squared, and we try to minimize this. This is also the sum squared error, correct?
Yes.
And minimize this with respect to X, and we get our solution. And we also saw in the last lecture that X will be equal to A pseudo inverse B. Okay, that was the original solution. Now, before we proceed with the proof, here is one thing that you should keep in mind. I have this block vector AB. It's another block vector, okay? It's nothing to do with this B, just AB. And what's its L2 norm squared? L2 norm squared of this vector is equal to the vector transpose times the vector, right? Which is, how do I transpose this block vector? I take the transpose of A and the transpose of B, and then I rewrite this vector as a row vector. So A transpose, B transpose, AB, right? This is my squared L2 norm, which is equal to, let me now proceed to do the multiplication. A transpose A plus B transpose B, which is equal to, what's A transpose A? L2 norm of A squared. What's B transpose B? L2 norm of B squared. Whence, if I take this block vector here, AB, its L2 norm squared is the L2 norm square of the upper block plus the L2 norm squared of the lower block. Okay, this observation you should keep in mind. Okay, an example will make it clear. This is C. C, L2 norm squared of C is 1 squared plus 2 squared plus negative 2 squared plus 0 squared plus negative 4 squared. That gives us 25. Now, let me divide C into two blocks, C1 and C2, where C1 is the upper half, 1 to negative 2, and C2 is the lower, not upper half, but upper part. They're not equal halves. And second part is 0, negative 4. So C is C1, C2, correct? What's C1 L2 norm squared? 1 squared plus 2 squared plus negative 2 squared, that's 9. And what's L2 norm of C2 squared? That's 0 squared plus negative 4 squared, which is 16. 16 plus 9 equals 25, right? So if I express this vector C in terms of C1 and C2, two smaller vectors, then squared L2 norm of C equals squared L2 norm of C1 plus squared L2 norm of C2. Are you guys with me on this?
Yes.
Yes.
And now that's the trick that I'm going to use here. So solving Rx is equal to C1 yields the same solution as the min norm solution, or Ax equals B. This is the overdetermined system. Okay. Now this phi of x, if you remember the last lecture, this is what we wanted to minimize, which was equal to L2 norm of squared L2 norm of the residue, the error, R transpose R. That's where R was B minus AX. Correct? Now, phi of x is B minus AX L2 norm of this square, and minimizing phi of x would give us the min norm solution, correct?
Yeah.
From the last lecture. Now, let me replace A with the full QR decomposition. So this is equal to B minus full Q R0 X L2 norm of that squared. Now, we know that unitary matrices preserve norms. So for any vector X, not just this vector, any vector X, norm of Qx will be equal to norm of X, right? We saw that for as one of the properties of unitary matrices. Unitary matrices preserve the norm. So what I do is this vector here, okay, what I'll do is I'll pre-multiply it with Q transpose. Instead of Q, you can pre-multiply it with Q transpose. If Q is unitary, then Q transpose is unitary too, right? So pre-multiply both this with Q transpose, and it would preserve the norm because Q transpose is a unitary matrix. So that's what I do. P of X is this. What I do is I pre-multiply this vector inside with Q transpose. So I have Q transpose V minus Q transpose Q R0X norm of that squared. Okay. Now Q transpose Q equals the identity matrix. And what's Q transpose B? I call it C. So I have this is equal to Q transpose B is my C, which is now this C1, C2. I express C as this block vector here, C1, C2. And this Q transpose Q, I just drop because it's the identity matrix. I have R0X here. And then this I simplify, it becomes C1 minus Rx and C2 minus 0x, which is C2, L2 norm of this squared. Are you guys with me?
Yeah.
I need some questions, guys. I know some of you might be lost. Either that or a couple of other more confirmations that you guys are with me.
Yeah, things are clear up to now.
Okay, good. I didn't hear you loudly, but that's okay. I think I heard a yes. Couple of yeses. Okay, so this is what I have. And then this is a block vector, and I want to find the squared L2 norm of this. What do I do? Using the approach that I illustrated previously, I can take the L2 norm of this squared and the L2 norm of this separately, square them, and then add them up together. So this is equal to upper block C1 minus Rx, L2 norm of this squared, plus lower block C2, square norm of C2. Okay, so this is my expression for this sum square error, P of X, that I want to minimize. Okay, now how do I minimize? And with what do I minimize? With respect to X, correct?
Mm-hmm.
Everything else is fixed. So when I minimize, you see, I have sum of two squares, right? So what's the minimum possible value I can get? I can make this equal to 0. And this will be C2, norm of C2 squared, right?
Yes.
And that's the minimum value that I can get when I make this equal to 0, the first term here. Okay, so I simply solve Rx equals C1. And this gives me the minimum norm solution. But solving this Rx equals C1 after doing the QR decomposition is the new method that we are seeing. So both using the QR decomposition and the min norm solution, which you can solve using pseudo inverse, will give you the same answer, same solution. Okay, both are equivalent. Questions?
No, it is clear.
Okay. Now, we'll go to back substitution. So how do we solve an expression like this where R is upper triangular or lower triangular? Okay, when this R here, or in fact, any A here, if this A is lower triangular or upper triangular, then solving simultaneous equations like this is very easy. Why is that? First of all, I've told you in the past that inverting a lower triangular or upper triangular matrix requires an algorithm that has a lower complexity than an algorithm that would invert any arbitrary matrix. But here's back substitution. This is how you solve. So I have Rx equals C1 actually, right? But I've just dropped the subscript 1 here. So I want to solve this. Rx equals C, and R is my upper triangular matrix. I will start from the bottom and then work my way up. Okay, so first I start with the bottom. 0x1 plus 0x2 plus 3x3 equals negative 6. Or 3x3 equals negative 6. So what's x3?
-2.
Negative 2, right? I took advantage of the fact that there's only one non-zero coefficient here, which is the 3. Everything else in the bottom row is 0. Okay, now I know that this is negative 2. I go here, and here 0 is getting multiplied by 1, and 2 is getting multiplied by x2, which I have to solve. And this 1 is getting multiplied by x3, whose value is now known. Okay, so what I have is, if I go from the bottom, one step up, I get to row 2, I have this. 0x1, drop it, 2x2 plus x3 equals negative 6. And we know that x3 is negative 2. So what is x2?
-2.
So x3 is negative 2. So solving, what do we get? x2 equals negative 2. Now I know x2 and x3. The values are known, negative 2 and negative 2. Now I go one step further up, which now brings me to the topmost row. And I can read it off. All the values except x1 are known. So let me read it off. What do I have in row 1? Twice x1 negative x2 plus twice x3 equals negative 4. Whence, replacing x2 and x3 with these values, I have twice x1 plus 2 minus 4 equals minus 4, or x1 equals minus 1. So this is back substitution. I did not give you an algorithm, but you can see manually how the algorithm would work. Right? All you have to do is start from the bottom and work your way. Solving for one x, scalar x at a time. So my solution is x1, x2, x3 is negative 1, negative 2, negative 2. Okay, so this is my back substitution algorithm. And now, if you recall, in one of the previous slides, I told you that for the math, for proving this, I use full QR decomposition for the proof that the solution obtained is the same as the that obtained from the min norm one and the sum square error minimization approach. They give you the same solution. I used full QR decomposition for this proof, but when in practice doing solving an overdetermined system using QR decomposition method, we don't have to use the full QR decomposition, right? Because we are dropping the C2 anyways. And so we're simply solving for our x equals C1, right? And so, so we can use the reduced QR decomposition here. Since only C1 is being used, we are ignoring the bottom rows. Therefore, we can simply decompose A into this Q here, which is a tall matrix of a smaller size, less number of columns, and this R, which is upper triangular, and simply solve it like this. QRX, this is this Q here. QRX is B, or RX is Q transpose B, which is simply C1. Okay, so that's how you would solve it. You don't have to do the full QR decomposition. Okay, are you guys with me?
Yes.
Yes.
Now, what we will look at is one simple algorithm called the Gram-Schmidt orthogonalization algorithm. And this algorithm does the reduced QR decomposition. Okay, it's a very simple algorithm. So let's see. This is the reduced QR decomposition. A is a tall matrix, M by N. It has more rows than columns. M is greater than N, and we can express this in terms of its column. Each of these columns is M, as in Missouri, M dimensional, and we have N such columns. And this is the reduced QR decomposition. This Q here is also a tall matrix of the same size as A, and its columns are all unit vectors and mutually orthogonal to one another. But this is not a unitary matrix, right? Because it's a tall matrix. I've dropped all the other columns that the full QR decomposition will provide. And here, this is a upper triangular matrix. Excuse me. And so this is the reduced QR decomposition, right? And this Gram-Schmidt orthogonalization method would obtain this reduced QR decomposition of A. So step one, what I have colored in blue is all the quantities that are known, and the unknown quantities are in red. Okay. Now, what I'll do is in each step of this approach, I will use a column. I'll start with the leftmost column, equate the left side and the right side in the first step. In step two, I'll use the second columns. In the third step, I'll use the third column, and so on. Okay. And so what I'll do is in the first step, all these elements in the first column here, I will find out. And this A1 is known because the matrix A is given, right? So doing the multiplication here, I see that A1 left-hand side is equal to Q1 R11 or R11 Q1, right? Agreed?
Yeah.
Yes.
Plus 0 times Q2 plus 0 times everything else here is 0. Okay. So A1 equals R11 Q1. Now, R11 is just a scalar. So Q1 is a unit vector, and A1 is a scalar times this unit vector. So they are in the same direction, right? All that's being done here is Q1 is being scaled appropriately by this scalar R11, and that gives me A1, right? What's the length of Q1? 1, because it's a unit vector. L2 norm is 1. What's the L2 norm of A1? This R11, correct?
Yes.
Right?
Yes.
So R11 is the L2 norm of A1. And Q1, because they're both vectors, being one, the relationship between them is Q1 times a scalar is equal to A1. So once I have R11, I divide A1 with R11, and that gives me Q1, right?
Yes.
A1 is known. So now from these two expressions, I have determined Q1 and R11. Are you guys with me?
Yes.
Well, there's an example. So this is my A. Step 1, I use A1. This is 1, -1, 1. And R11, let's ignore this for now. R11 is L2 norm of this, A1. 1, -1, 1. The L2 norm of this is square root of 3. And Q1 is 1 over R11, which is 1 over square root of 3 of A1. 1, -1, 1, which is this. So this is my Q1, and this is my R1. And these are all zeros. So I found out these values now. Now, step 2. In step 2, see, what I'm doing is I'm working my way from the left to the right. So the first column, now these elements are known in the first column. On the right-hand side too. So now these elements here are known. Okay. And here, well, all these elements are known, but I've colored this blue because that's the one that I'm going to use, not AN. Okay, so both sides, we're looking at the second column. Now, Q1, R1 are known. Okay, so now let's look at the second columns on both sides. A2 should be equal to Q1 times R12 plus Q2 times R22 plus the rest are all zeros. Q3 times 0 plus Q4 times 0, so we'll ignore the rest. So we need to find these R12, R22, and Q2. Let's do the multiplication. So A2 is equal to Q11 R11 plus Q2 R22. Okay, or I bring the scalars on the other side. So A2 is R12 Q1. Q1 is known, and from the previous iteration, from the previous step. And A2, all these, the A matrix is given to us. So it's known. Plus R2 to Q2. Now, let's see that graphically. These are Q1 and Q2 are unit vectors. And they're both mutually orthogonal to one another. And A2 is a linear combination of Q1 and Q2. So this is my A2. This length here, if this is since this is a unit vector, this is A2. This length is R12. If I take this projection of A2 along Q1, this length is R12. And the projection of A2 along Q2, which is unknown, Q2 is unknown, is R22. But Q1 is known, right? Q1 is known. And since Q2 is orthogonal to Q1, what happens if I pre-multiply both sides with Q1? Both sides I multiply with Q1. What happens? On this side, I get Q1 transpose A2. What happens to Q1 transpose Q1?
1.
It's a unit vector, so 1. And what's Q1 transpose Q2?
0.
0, because Q1 and Q2 are mutually orthogonal, correct?
Yeah.
So I do this pre-multiplication. So I get Q1 transpose A2 equals R12 Q1 transpose Q1 plus R22 Q1 transpose Q2. Sorry, Q1 transpose Q2, which is equal to, this is 1. Q1 transpose Q1 is 1, and Q1 transpose Q2 is 0. So this term becomes 0, this term becomes R12. So Q1 transpose A2 is R12. In fact, from the here graphically, how do I, this R12 is a projection of A2 along Q1, right? So Q1 transpose A2 will give you this the norm of the projection, the length of the projection R12. So I get R12. And then in general, I'll keep going from these until I'll hit the diagonal element. Okay, I'll go from top to bottom. So here, the second one is the diagonal element anyway. Okay, so step 2, I got R1, 2, and okay, so now let's see. Since I got R1, 2, and Q1, so I know this whole vector, right? And what remains is this Y2 here. So R12 is Q1 transpose A2. I obtained Y2 equals A2 minus R12 Q1. The projection of A2, this vector here, from this whole of this length R12 here. This, if I remove from A2, this is R12 Q1. If I remove from A2, I'll get this vector here, right, which is Y2. So here, if you look here, you'll observe the same thing. So if I, what's A2 minus R12 Q1, R22 Q2, right? This R22 Q2, a vector from this origin here to this point here. That's my Y2, this guy. And Y2 is along the direction of Q2, correct?
Yes.
And that's equal to this R22 Q2.
Yeah.
So R22 Q2 is Y2. Friends, since Q2 is also a unit vector, the length of Y2, L2 norm of Y2 gives me R22. And if I normalize Y2, since Y2 is the same direction as Q2, I just divide Y2 by R22, which is its norm. I get a unit vector in this direction of Y2, which is Q2. So Q2 equals Y2 over R22. So I've solved this and this, and I also got my Q2. Are you guys with me?
Yes.
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 Okay, so this is step 2. Now we can generalize. In step K, we will be looking at the kth column on the left hand, on all three matrices actually, right? And so this is step 2 in our example. So this is my matrix A. We have already solved for this and this. This is R11 and this is Q1. And now we have to find Q2 and R12, R22. So R12 is Q1 transpose A2, which gives me 2 over square root of 3. R22 is, so I take Y2 is A2 minus R12 Q1. And since I just found out Q1, sorry, R12, I replace the value here. I get this. So R22 is this norm here, square root of 2 over square root of 3. Is the norm of this vector here, square root of 2 over square root of 3. And what's Q2 now? I'll basically take this vector here and divide it by its L2 norm, which is R22. So this is Y2 divided by R22 gives me this 1 over 6, square root of 6, 1, 2, 1. Okay, and then for this example, I'll have the third and last step, but now let's generalize. So now I am in the kth step of my Gram-Schmidt orthogonalization. Now, at the kth step, since I'm moving from left to right, I have solved Q1 and Qk minus 1, correct? And I already know these values. On all the first k minus 1 columns of this matrix are also, I know these values, right? And so what I have to find is this Qk here and these coefficients R1k until RKK. So we need to find R1KK, R1K, excuse me, R2K until RKK and QK. Okay, and now let's compare left and right hand sides, the kth column. AK equals kth column, right? So Q1 R1K Q1 plus R2K Q2 all the way until the ith column here, where I is less than K. Okay, I is less than K is RIK and QI. Something here all the way to last one will be RQK, RKK. Okay, so remember that I is an index that's less than K. It's between 1 and K. Now, pre-multiplying both sides with QI. QI is any one of these Qs. Okay, Q1, Q2, Q3 until QK minus 1. Any one of these known quantities. QI transpose AK equals, what do I get here? I pre-multiply both sides of this expression with QI. One of these blue Qs, which are known. What do I get? On the left-hand side, I get QI transpose AK. What happens on the right-hand side when I do this pre-multiplication?
RIK.
All other terms except QI will be 0.
Exactly. So QI transpose Q1 will be 0 because QI and Q1 are 0, assuming I is not equal to 1. Likewise, QI transpose Q2 will be equal to 0, right? So all these terms will, in fact, this is unknown. QK is unknown, right? But we know that QK will be orthogonal to QI. So even though this is unknown, even though QK is unknown, we know a priori that it is orthogonal to QI, right? So QI transpose QK will again be equal to 0. In fact, all the terms will become 0 except this one. QI transpose QI will be equal to 1. So what we will be left with is RIK. So I do this multiplication. I pre-multiply both sides with QI transpose. All I have remaining is RIK. And all these QIs, Q1, Q2 until QK minus 1 are known, correct? And AK is also known. So all these RIKs I can effectively find. QI transpose AK equals RIK. So for I equals 1 through K minus 1, I have RIK equals QI transpose AK. Are you guys okay? No questions?
Yes.
Yeah.
Okay. And now what I have done is I have found out R1K, R2K, all the way to RK minus 1K, except this RKKQK. All these are now known quantities once I've found those out, except the diagonal, okay, QK here and RKK. So what remains is this. AKK, if I subtract all these known quantities, minus R1K Q1, minus R2K Q2, all the way to minus RK minus 1K QK minus 1, what remains is YK, which is actually RKK QK. So YK is a K minus summation I equals 1 through K minus 1 RIK QI. Okay, this is what remains. And now this YK, so I've basically brought all the known quantities to the other side, the left-hand side becomes a subtraction, and I've only left with RK RKK, QK on the right hand side. Hence, RKK, QK equals YK. How do I find out RKK? Well, YK can be computed, right? Because now I've determined all these RIKs, right?
Mm.
And so YK can be computed. Knowing that QK is a unit vector, RKK is the L2 norm of YK, right? Hence,
Oh, yeah.
RKK is the L2 norm of YK, and a unit vector along the direction of YK will be QK. So QK equals YK over RKK. Okay, and so this gives me the kth step of the Gram-Schmidt orthogonalization algorithm. Now what I'll do is, this is my RIK, is QI transpose AK, and RKK and QK RK. So this is known. Now I'll fill out these values and then proceed to the next step, QK minus K plus 1 all the way until N. This is the example. So Q3 is unknown. In the first step, I find R13, R23, Q1 transpose A3, Q2 transpose A3, and this gives me these values. Replace them, and then take the Y3 would be A3 minus R13 Q1 minus R23 Q2. So this is my Y3 here. And so take the L2 norm of that, gives me R33. Where's R33? Oh, this one. And 1 over R33 times at Y3 will give me this. Okay, so this is the QR decomposition of this simple 3x3 matrix A. Okay. Now, remember, before we do the Gram-Schmidt algorithm, write down the steps of the algorithm. So, right before the kth iteration, these are the quantities that are known. A1 through AK are the one that we're going to use. All of this is known actually, but here on this side, Q1 through QK minus 1 are known, and here these diagonal elements all the way up till column K minus 1 are diagonal and upper triangle elements are known. And YK is AK minus summation RIK QI, where I goes from 1 to K minus 1. You understand this, right?
Yes.
So this is the input. So I have a for loop here. I work my way from the leftmost column, 1, all the way to the last column, n. For k equals 1 through n, what do I do? Find the residual. Yk equals, well, residual is this, right? So what I'll do is, I'll initialize yk to ak. And then what I do is, I'll put this in a for loop, another for loop here, for I equals 1 through k minus 1. And then each time I loop through this inner for loop, I will subtract one term RIK QI from it, from YK. Okay, so now RIK is QI transpose AK. So I find RIK, and then I subtract one term RIK QI from my YK. Okay, so YK, I started off with AK. After this loop is done, I find all the RIKs here using these expressions until R K minus 1K, this one but the diagonal just before this RKK here. I find all of these, and then YK equals, at the end of this for loop, I'll have subtracted all these terms from AK. that will be the actual yk, right? Yk I initialized to ek, and then I'm subtracting all the terms here. I subtracted that term, and then, so this is my inner for loop. You guys are with me as far as this inner for loop is concerned?
Yes.
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 And then what do I do? What will be the last step outside this for loop?
RKK.
Compute R.
RKK will be equal to the norm of YK, right?
Yeah.
And QK will be YK divided by RKK, right? Because QK and YK will be in the same direction. So RKK is the L2 norm of YK, and QK is YK divided by RKK. End. This is the basic Gram-Schmidt algorithm. Any questions?
No, not yet.
No, Doctor.
Okay. Now, what's an upper bound in terms of n of this algorithm? K equals 1 through n. So the outer loop loops n times. The inner loop actually loops less than n times, but an upper bound, a loose upper bound will be n squared, right? But you should also keep in mind that here, these are vectors. In MATLAB, you tend to forget, but this will be another for loop if you want to use C or Java or anything, right? Which can handle only scalars. So this is another for loop here. Okay, so it's more than n squared. It's less than n cubed for sure. I don't remember what exactly is the complexity of this. Okay, so now a review. Full QR decomposition. Here, Q is a unitary matrix, a square matrix, and this here is upper triangular matrix and a lower matrix of all zeros. Okay, and A is a tall vector. R here, R0 here combined is a tall vector. And here, Q transpose equals I, and Q transpose Q is also equal to I. Okay. This is a little misleading because this size of Q is actually this. So these two figures should have been a little bigger, but they need to fit into the slide. Now, in reduced QR decomposition, this is what we have, right? This is my reduced Q. I drop these columns from my Q here, and I also drop these zero elements from the other matrix. So what remains is the upper triangular matrix here, and this is a matrix Q, which is not unitary because it's a tall matrix, correct? And so Q transpose will not be equal to I because the rank of this Q transpose will be what? It will be M, number of columns of A. It won't be N, which is the number of rows of A. So this won't be equal to I, but Q transpose Q will be equal to I. This is the smaller I. For overdetermined systems, how do we solve? Like taking the full QR decomposition, we want to solve Ax equals B. What we do is do the QR decomposition, the full QR decomposition of A. We get Q, R0 here, X is B. And so then what we do is, and on this, then we pre-multiply both sides with Q transpose. We get R0X is approximately equal to Q transpose B. And we express this product, Q transpose B, this vector here, in terms of two blocks, C1 and C2. the size of C1 is the same as the size of X. Whence X equals R inverse C1. How will you do this? Using back substitution. You don't actually have to take the inverse, but computing the inverse of an upper triangular matrix is actually just a variation of the back substitution algorithm. And this yields the least square solution. Phi of x is b minus ax squared, which is equal to, we showed that this was equal to C1 minus Rx and C2 L to norm of this squared. And so this is my phi of x, right? We were able to show that phi of x can be expressed in this form. This is the sum square error, or the square norm of the error b minus ax. And how do we minimize this? By letting this C1 minus Rx be equal to 0, right? So we have to solve this. Rx is C1 here, the same thing as this. Gram-Schmidt orthogonalization algorithm. So we work from the leftmost column rightwards. And so in the kth step, we have the kth column and everything else before. All these q's are solved for, and these r's are also solved for. We have to solve for these r's in the kth column here, and we have to solve for qk. And so this is the Gram-Schmidt algorithm. What we are doing is, well, I think you understood. So the blues are what are known here. So Rik, I'm finding out within this inner for loop. R1k, then R2k, then R3k, and so on. Rik, and I'm using these q's here, qi, with the, since I is from 1 to k minus 1, these are known. And so qi transpose ak, you can easily compute Rik. And what I'm doing is yk equals ak, and at each time I'm subtracting an Rik qi from my yk. So at the end, yk is a vector in the direction of qk, and so I take the L to norm of yk, that's rkk, and a unit vector along the direction of yk becomes qk. So I find out all these r's and this q. Any questions?
No, doctor.
No.
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 Okay. Now, for numerical reasons, any algorithm, any inbuilt algorithm to do Gram-Schmidt will actually be using a modified version of this, but we don't need to know that. Okay. Gram-Schmidt orthogonalization is often used in proofs in various places. So that's something that you can use. Okay, so we will meet at 6:30 for a review. Okay, let me stop the video. So, 6 or 6:30, when did we decide?
Guess it's 6:30.
6:30. Oh, okay. I thought it was 6, but 6:30, that's fine. So we'll meet at 6:30 then. Now, I'll send out a separate Zoom link for our 6:30 tutorial. One thing, I wanted to show you something, on in MATLAB, but my Office desktop is down there, so it crashed, and they're fixing it up. So most likely I won't be able to show you anything in MATLAB. Okay.
Okay.
Anyways, so see you then.
Okay, thank you, doctor.
Thank you.
Thank you.